Okay, so in this problem, we are going to be determining the concentrations of ions provided that a given ionic compound has been given. So the question says it like this. They're saying determine the concentrations of the ions in each of the following compounds below. We're seeing 2.5 molar of sodium sulfate, 0.125 molar of calcium hydroxide, 1.5 molar of ammonium carbonate, and lastly 0.5 molar of the potassium phosphate. So all these are the correct chemical formulas for these compounds, but cases can be given whereby these chemical formulas have not been shown, have not been displayed, but the chemical names of those compounds have been given. Maybe say sodium sulfate, calcium hydroxide, ammonium carbonate, and potassium phosphate. Like these chemical formulas have not been given. So you'll be required to write the correct chemical formulas for these things. So in the case whereby maybe you have challenges in writing chemical formulas, let me just take my time to just explain how these chemical formulas were derived. Okay? So sodium sulfate. Sodium is in group 1, so its valency is 1. The sulfate is a radical. It's made up of one sulfur and 4 oxygen atoms chemically combined together, and its valency is fixed. It's always 2. So 1 sodium, that is the valence of sodium here, is going to be 1. The valency of the sulfate is going to be 2. So these numbers need to be swapped. The 2 on the sulfate is going to come on the sodium, and the 1 on the sodium is going to come on the sulfate. So what we're going to have is Na. The 2 is going to be dropped here. You can open your brackets and then you write your entire sulfate, and then the 1 is going to be put there. But in most cases we normally don't show the 1, so this can just be better written as Na, 2, and then SO4. So this is how your sodium sulfate looks like. This means that there are 2 sodium atoms which are in a bond with the sulfate. This is what this means. The other one is calcium hydroxide. On our periodic table, calcium is in group 2, so its valency is 2. The hydroxide is OH. It's also a radical. The definition that you can give for a hydroxide can be defined as a deprotonated water molecule. The opposite ion to the hydroxide, we have a certain ion which we call the hydronium ion, which is H3O+. We have OH- as well. So this is what we call a hydronium ion. This is what we call a hydroxide ion. This one is a protonated water molecule. This one is a deprotonated water molecule. It's like H2O is like this. A hydrogen ion can be called a proton. So when I say protonated, then it means that there is a proton that is being added to a water molecule. There is a hydrogen ion which is being added to the water molecule, which is going to make us have H3, because originally it was H2. When I say deprotonated, then it means that I'm removing a hydrogen. That is why we are having 2 water molecules here. If I remove 1 water molecule, 1 hydrogen, what we're just going to remain with is OH. This one is responsible for the properties of an acid. This one is responsible for the properties of a base. But again, time is going to come when we will explain these things in much more depth, acids and bases. But for now, let's just continue with the basics. So the hydroxide here has a valency of 1. The calcium has a valency of 2. We can swap these numbers. When we swap these numbers, what we're going to have is calcium. There is a 1 here, but like I've said, most cases we don't show it, so you just open your brackets, OH, and then 2, in that way. The same thing also applies when you're talking about your ammonium carbonate. Ammonium is a radical, and its valency is 1. The carbonate is a radical as well, whose valency is 2. So if we swap these two numbers, this is going to be NH4, 2, and then the carbonate, the CO3, is going to be written there. And lastly but not the least, we're also having the potassium phosphate. Potassium is in group 1, so valency is 1. The phosphate is PO4. This is how we write it, whose valency is 3, which if we interchange, the answer is just going to be K3 and then PO4. The phosphate is an inorganic substance which is mostly utilized in the formation of adenosine triphosphate, ATP, a very, very high energy compound that is going to be generated in the mitochondria during respiration. But again, that part is going to come when we're going to say much on this one in biology. So this is how your potassium phosphate looks like. Your calcium hydroxide, your sodium phosphate, and your sodium sulfate, and your ammonium carbonate. So this is how we were having them. Now, it's very much important that you learn how to write your chemical formulas. Because if your chemical formulas have not been written correctly, you're going to be having challenges in determining the molarities of these ions. The sodium sulfate is made up of 2 ions, sodium ions and sulfate ions. We are going to see that in this compound here, there are 2 sodium atoms. So if you are going to write those ions now, you are going to write them in this way. The 2 which is down here is going to be written as the coefficient. This is the whole reason why we are writing 2Na and then plus 1 plus, because it has a valency of 1. Take note, if you write it in this way, this is wrong, because you're trying to tell them that you are having 2 sodium ions which are in a bond with each other. And one thing that you need to understand is that these sodium ions are not in a bond with each other. They are free, they are independent, they are free to move, they are free to migrate. So if you write it in this way, then you're telling them that those sodium ions, 2 sodium ions, are in a bond with each other, which they aren't. So you rather need to put a 2 in front, and then you write the sodium ions to show them that they are independent. They are able to move freely on their own. Very important that you understand. So 2 sodium ions in that way. There is only 1 sulfate here. That's the whole reason why I'm writing SO4. Remember the 2? The 2 was the valency. But because it's a non-metal, it's negatively charged. So just a recap. Metal ions are referred to as cations. They are cathode ions because they migrate to the cathode which is negatively charged. They are positively charged, so they're going to migrate to the cathode which is negatively charged. Remember, unlike charges attract each other. Non-metal ions like the sulfate ion here are referred to as anode ions or anions. Why? Because they migrate to the anode which is positively charged. They are negatively charged, so they are going to migrate to the anode which is positively charged. Hence the name anode ions. 2 sodium ions, 1 sulfate ion. Having understood this, it is from these same ions, these same values, the 2 and the 1, this is where we are now going to start introducing the molarities. This is what we're going to use to calculate the molarities. So if I write my brackets in this way and then I put my sodium ion inside, this means concentration of sodium ion. When I write these brackets like this and then I write my sodium ion inside, this means concentration of sodium ion. When I put my sodium sulfate inside these brackets, chemically speaking, I'm saying that I'm talking about the concentration of the sodium sulfate. So, concentration of sodium ions, concentration of sodium sulfate. If you notice, the sodium ion is having a stoichiometric coefficient of 2. So because it's having a stoichiometric coefficient of 2, it means that the molarity of the sodium ion is 2 times the molarity of the sodium sulfate. One more time. The 2 here on the sodium ions implies that the molarity of the sodium ion is 2 times the molarity of the sodium sulfate. So it's now more like extending to molarity ratios, provided that the volume here is maybe say 1 decimeter cubed. So more ratios can be converted into molarity ratios if the volume value has been restricted to just 1 decimeter cubed or 1 liter. So the concentration of sodium ions, the molarity of sodium ions is 2 times the molarity of the sodium sulfate. This is the whole reason why this is going to be 2 times 2.5, the original value of the molarity of the sodium sulfate, 2.5. So 2 times 2.5, the answer is just going to be 5 molar. And that's it. You have determined the molarity of the sodium ions. If you look at the mole ratio between the sodium sulfate and the sulfate, you're going to see that they are having a 1-to-1 mole ratio, which means that the molarity of the sulfate ions is equal to the molarity of the sodium sulfate. And having given the molarity of the sodium sulfate, which is 2.5, then it means that the molarity of the sulfate ions are also going to be 2.5 molar. So do you see why it's important for you to write not only just the correct chemical formulas, but also ionizing them in the right way? Because these stoichiometric numbers, stoichiometric values, are the ones which are going to determine what the molarity of your ions are going to be. The sodium ion is having a 2, so it's 2 times the molarity of the sodium sulfate. The sulfate ion is having a stoichiometric coefficient of 1, so it's 1 times the sodium sulfate in that way. The same concept can be applied for calcium hydroxide. 1 calcium is being in a bond with 2 hydroxides. So if we ionize this one, we are going to see that there is a calcium ion. There is only 1 calcium here. So calcium ion, calcium valency 2, it's going to have a positive charge. It's a cathode. It's going to have a positive charge. This 2 is working specifically for the hydroxide. So like I did for the sodium, I will bring the 2 in front of the hydroxide. So it would be very wrong for someone to just write it in this way, OH, there is a 2 down here, brackets like this, and then someone just writes like a minus like this. This is very, very wrong. Very wrong. So rather, take the 2, put it in front, so that this is going to be 2OH, and then minus in that way. Then you're talking about 2 hydroxide ions now. So calcium 2 plus, 2 hydroxide ions in that way. Again, same thing. The mole ratio that is between the calcium and the calcium hydroxide, the mole ratio is 1-to-1, which means that the molarity of the calcium ions is going to be equal to the molarity of the calcium hydroxide which has been given. And the value according to the question is 0.125. So the molarity of the calcium ions is equal to the molarity of the calcium hydroxide, because the mole ratio is 1-to-1, so the value is just going to be 0.125. The mole ratio between calcium hydroxide and the hydroxide ions here is 1-to-2. The hydroxide is having a stoichiometric coefficient of 2. So like I had explained here, the concentration or molarity of the hydroxide ions is 2 times the concentration of the calcium hydroxide. Hence, this is going to be just 2 times 0.125 molar, which is going to be 0.25 molar in that way. So the 2 here implies that the concentration or molarity of the hydroxide ions is 2 times the molarity or concentration of the calcium hydroxide. So the value is just 0.125 as given. So it's going to be 2 times 0.125, which is just going to be 0.25 molar. If we extend it here to the ammonium carbonate, it's the same concept, same idea, same thing. The 2 here is on the ammonium only. So I'll bring the 2 in front here and we're going to have 2NH4 plus. The ammonium ion acts as a cathode ion. It acts as a cation. It also migrates to the cathode, which is negatively charged. So anytime you're writing your ammonium ion, treat it as a metal ion. It has a positive charge. So 2NH4. There is only one carbonate. A carbonate is made up of 1 carbon and 3 oxygen atoms combined together. So again, it would be very wrong for you to just say the same way it is CO3, you try to bring the 3 this side and then you're going to say 3CO. That's going to be very wrong, because carbon and oxygen are 2 different things, and moreover this 3 is only working on the oxygen, not on the carbon. So it's very wrong for you to want to take this 3 and make it a coefficient. The carbonate has a valency of 2 and it's negatively charged. When one is positive, the other one is supposed to be negative. Again, same interpretation, same thing. Because the ammonium is having a 2, it means that the concentration of the ammonium ion is 2 times the concentration or molarity of the ammonium carbonate. This is the whole reason why I'm saying concentration of the ammonium ions is 2 times the concentration of the ammonium carbonate. The value has been given to be 1.5, so this is going to be 2 multiplied by 1.5, which is going to be 3 molar. If we look at the mole ratio between the carbonate and the ammonium carbonate generally here, you're going to see that the mole ratio is 1 to 1, which means that the concentration of the carbonate ions is equal to the concentration of the ammonium carbonate, which is going to be the same value, 1.5 molar. So it's basically just getting these values, the stoichiometric coefficients, and then multiplying them with the molarity value in the question given. And then lastly, but not the least, we are seeing our potassium phosphate. There are 3 potassium ions there and 1 phosphate present. The valency of the phosphate as established is 3. It's a non-metal ion, so negative charge. The potassium is a metal. It's found in group 1. It's having a 1 plus oxidation number, or a positive charge here. Again, there is a 3, there is a 1. This 3 implies that the concentration of potassium is 3 times the concentration of the potassium phosphate. This is what I have just written here. So it's going to be 3 times 0.5. And 3 times 0.5 times is just going to be 1.5 molar. The phosphate and the potassium phosphate overall are having the same stoichiometric coefficients, which are 1. So because the mole ratio is 1 to 1, the concentration or molarity of the phosphate ion is equal to the molarity of the potassium phosphate. This is what I've just written here. Molarity of the phosphate ion is equal to the molarity of the potassium phosphate, whose value is just going to be 0.5 molar. So this is how questions as well under concentration or molarity can be given to determine the concentrations of these ions. So I believe what I've explained here has made sense. A lot of practice on this will make you understand these things better. So practice makes perfect. So thank you very much.